Good to know. Thank you, John. Let's see what we got.
Right out of Star Wars, Bill.
What?
Something looks like it's right out of Star Wars.
I grabbed that long ago and I still like it.
No, it doesn't look like that.
It doesn't look like that.
And that's the pet peeve of every astronomer's view of science fiction movies is the asteroid belt being portrayed like a cloud. Okay, so what we got going tonight is Dr. Bill Bottke will be giving his presentation, and then Leonard's going to do his PowerPoint presentation, and then we're going to show some pictures that we got from John Asselos and stuff on this computer, and then John Williams, who is our host down in Santa Fe, has some stuff people have sent him, and he'll be showing that. And then at the end, we'll just kind of open it up if any Zoomers or something have anything to say. So I guess that's it. Barb, come up and do the introductions.
Okay. See, do I need to make sure that?
Yeah,
I'm near the.
stand back here
Back here?
and
Okay.
face the microphone.
Okay, so thank you all for being here. And let me hand out some sky calendars. If there's not enough, then let me know and I'll email it to you. Those are left over from Halloween. We'll talk to you more. We had 80 Halloween trick-or-treaters at our house, but we'll talk to you more about that later. Want to thank the Mountain Messenger. He's always so wonderful about giving me an extra day to do my article. And want to thank the Coal Creek Canyon Park and Rec people who are our sponsors. And we're looking at possibly doing a December meeting. I think that would be probably the first Saturday or second Saturday in December. And what we might do, although I haven't talked to John Williams about this, is maybe have him and Leonard sort of sum up the year with what we've seen, both in astronomy and space exploration, and then what to look forward to next year. Maybe could we show, if we do that first Saturday, I think it's the 3rd or 6th or something, but
13th.
or the 13th.
That's the second.
Would people want to come to that? Or are you too busy in December? Can we see it? Maybe, yeah, maybe, just maybe, so you don't need to say. Okay, yeah, so maybe we'll do that. We'll have it in the Mountain Messenger. So we are very honored to have Dr. Bill Bottke here for our speaker. And as you probably all know, because you probably got our email, but he's the executive director of the Solar System Science and Exploration Division at Southwest Research Institute in Boulder. And he's going to talk to us about the NASA OSIRIS-REx mission. And Leonard and I were actually in Dugway in Utah when that capsule came back. So we have a special interest in that. And also about the Lucy asteroid mission, Psyche and Surveyor, and also the Emirates mission to the asteroid belt. And he got his PhD at University of Arizona, and also is an expert on the origins of the moon. And although he's not talking about that tonight, maybe we can get him to come back again. Talk about that. But he's come all the way from Longmont, and that's about an hour from now, from here. So we're really honored that he was willing to come all this way to give a talk in person. And then we have a whole lot of people on Zoom too.
Oh, great.
So
Well, thank you. Thank you very much for that very nice introduction. Yeah, I had to come all the way from the distant wilderness of Longmont, right? So but no, it was a nice. I've actually never been up here, so it's actually kind of fun to see this up here. I've heard it talked about before, and Bob Grimm lives up here, and I've heard about this. So this talk, I kept trying to put stuff in this talk, and I kept putting stuff in. So it's more than I probably have. So I may have to skip through some of it fairly fast, or skip a few things. But there's a lot of fun stuff in it, and So hopefully you'll enjoy this. I enjoy talking about small bodies. I've been working on small bodies most of my career in some fashion. And I thought what I'd like to do today is this is sort of the fleet of NASA spacecraft that we have that are doing interesting things with small bodies. Yes.
I messed up. I forgot to share screen. So
Oh,
that means the Zoomers aren't seeing this.
okay. So we can go back.
My apologies.
We'll go back to the intro screen so they won't miss anything.
Okay. You go down.
Wait, and Bill, you got to see a little bit of Aurora from Longmont.
I did. My wife and I drove almost from Longmont, almost to I-25. From there, we kind of found a dark patch and we were able to see a little bit, but it sounds like some others from Longmont got better views than I did. I think we went out kind of between some of the really spectacular things. So, but we at least saw it. I'd never seen the Northern Lights before, so it was nice to see it. Minnesota's not a good. I grew up, as you'll tell from my accent, right? Minnesota. I grew up in Minnesota. Minnesota is not a great place to see the Northern Lights because it's got clouds.
All right. We should be good.
Okay. All right. So now we'll begin again. Okay. So,
I will say one thing for the Zoomers.
Yeah.
The Zoom connection has dropped out a couple of times this evening already. Those of us in the hall, we're not going to notice. It's going to go fine.
That's why they should come in person.
So, yeah, we think the Zoomers ought to come here in person, but just be forewarned that the Zoom connection has been a little flaky.
okay.
Did I do this?
Barb forgot to mute.
You know, every Friday in our department, I often will run a science discussion for about 45 minutes. And like little AV things like this make me feel right at home. Right? So don't feel bad. I do this all to myself all the time. Okay. So we were talking about NASA's small body fleet. And I've been fortunate enough, you can see all these different missions here. I'm fortunate enough to be involved with 4 of these different missions right now. Okay, so OSIRIS-REx, which I'll talk about in just a second, the Lucy mission, the Psyche mission, and a mission that hasn't launched yet called Near Earth Object Surveyor. Okay, so this was an ambitious talk. I'm going to see if I can get through all these things. We'll see how that goes. And hopefully we'll have some fun along the way because I think there's a lot of interesting things to talk about. Okay, but I wanted to set the context a little bit about why is it interesting to study small bodies? Like, why do we care? Right? So to go that, we're going to go all the way back to the earliest times of the solar system. So let's go back to when the solar system was forming. So imagine our planetary system starting off at one point is just a giant cloud of gas and dust. Okay. We see this in the solar system. We see this around the galaxy quite a bit. These large clouds can collapse and create protostars, but they can also create disks of material. And that's what you're looking at here down at the bottom, a protoplanetary disk. Now, in that, what happens is you have all this gas and dust, which is going around the star, and small dust particles can collide with one another. And here's sort of just an example of what it might look like of two sort of fractal aggregates of dust colliding with one another. And when they do, they stick. Okay, and so things gradually start to grow and get larger. Dust starts getting more dust and they get larger and larger. Okay, and then eventually they reach sizes where life gets very interesting because then they can interact with the gas and they actually like to go to where the gas is having, let's say, high pressure zones. So we call these objects, when they get to maybe about a size of a millimeter or a centimeter or so, we call them pebbles. Okay? Not really a pebble, like you go outside and find a pebble. A pebble is never that size. But in solar system talk, pebbles are things between about a millimeter and a centimeter or so. So they go towards these high pressure zones, they can become concentrated. And when they do, life gets very interesting. So we'll go to the next slide here. Okay. And what happens is you take all this material, we'll see how this animation goes. You take all this material and just the self-gravity of all these small pebbles coming together can cause this sort of the concentration to collapse. Okay, so gravitationally it's collapsing, and this is the way we tend to make objects, or what we call planetesimals. Where planetesimal just means little planet. Okay, but ultimately this is how we make objects which are asteroids. This is how we make objects which sometimes we call Kuiper belt objects, but sort of the icy equivalent of asteroids in the outer solar system. They're made with, we think, by the same process. Okay, so a typical size that's made out of this process is about 100 kilometers. So at one point, many of the objects in the solar system were maybe the order of about 100 kilometers or so, and they were made by these collapsing clouds. Okay, so we start to make lots and lots of little things. Okay, Now we'll jump ahead. And then this is just sort of an animation showing you what might happen after that. So imagine making these swarms of planetesimals, asteroids in the inner solar system, and more icy things towards the outer solar system and the rest. And then what you're looking at here is on the x-axis, we're looking at the mass of the planet. So the higher you go on this plot, the more massive you are. Okay. And then on this axis, we're talking about distance from the sun. And astronomers like to use a unit called an astronomical unit, which is the distance between the sun and the earth. So that's where 1. So 1 corresponds to that distance. And we just use that as sort of an easy way rather than dealing in kilometers or furlongs or miles or whatever. Okay. So what you're looking at here is that small things are getting larger and they're bumping into one another. They're accreting, they're growing, and eventually we end up with a system in the inner solar system, which looks kind of like our system. We end up with a body that's about the right size for the Earth, about the right size of the Venus. We end up with maybe a Mars-sized object, and then we actually have some material that's left over, and some of that material may be sort of what we would call the asteroid belt, and that's going to be the most interesting part of this, okay? At least for this talk, okay? In the outer solar system, we have something similar happening, but then what happens is that if objects get large enough and they can interact with the gas enough, they can actually start to grab some of these pebbles that are making these planetesimals. They can start to grab them and form much larger objects than they can in the inner solar system. And so that's why we have Jupiter. This is why we have Saturn. These worlds get so big so quickly that then they're massive enough to grab a lot of gas. Okay, so this is where our gas giants come from. Okay, but you'll notice in the simulation, if you have a good eye, you'll see that while we make things like Jupiter and Saturn, you also make some objects that are about the size of Uranus or Neptune. But you notice we're not just making Uranus and Neptune, we're actually making a few more objects than that. So this
That
Okay. That's right. So in this simulation, we're making more than just Uranus and Neptune. We have a few extra of those objects. And that's going to be an interesting part of the story, and I'll tell that story a little bit later in the talk. So keep that in mind. Okay. Okay. So where are we at? So right now we've formed the planets, but we're interested in small bodies. So small bodies are essentially the leftover pieces. They're the building blocks of the planets, or sometimes, think about them as fossils of formation. Most of the leftovers are in this thing we call the main asteroid belt. And it's located between the orbits of Mars and Jupiter. And it contains about 1 million objects or so that are at least a half mile across. It's got some bigger objects too, but has lots and lots of bodies that are small. And then you notice if we take away the main belt, you can look onto the orbits where our planets are going, Mars and Venus and Earth and the rest, and you can see there's still swarms of bodies there, but not nearly as many. These are often referred to as near-Earth asteroids. They're the ones that are easiest for the visit, and sometimes they can hit the Earth and hit the Moon and hit the other worlds as well. Okay, so these are some objects, because they come so close to the Earth, they're very accessible for our spacecraft, and that's going to be an important part of our story as well. Okay, so what are little asteroids? If you see a little asteroid in space, so you go to it, where did it come from? So I was just telling you that most asteroids are 100 kilometers in size. Well, what happens in the asteroid belt is that these bodies from time to time undergo collisions. So here's sort of some animations about what that might look like. So here's a case where a 100-kilometer body is being hit by about a 20-kilometer body. Okay, you can see it's creating all sorts of fragments. And here's a simulation of where the fragments might go. And they fly a good distance away from the impact site. But after that, you could actually today in the asteroid belt find evidence for remnants of previous collisions because the fragments are all still sitting around there. Okay, sometimes we call these things asteroid families, which are fun. Okay? And some of these small objects actually have dynamical ways to escape the asteroid belt. And that's where our near-Earth asteroids come from. I'm not going to talk a lot about that dynamical process. That's a really interesting thing too. But for time reasons, I'm just going to jump along. Okay. So small asteroids, much smaller than 100 kilometers, many of them are fragments from collisions. Okay. So that's part of our story. Okay. So here's sort of a nice plot that was put together by someone from the Planetary Society, Emily Lakdawada. She took all these different asteroids we had and put them on one plot and then scaled them all the right size just so you can sort of see things. And you can see that our asteroids come in all sorts of different shapes and sizes. Okay, we would have a comet over here, but there's some other bunch of comets that are down here. But for the moment, we'll just concentrate on the asteroids. So what do we see? We see they have very irregular shapes because of collisions. They're covered with craters, again, because of collisions. And they come in sort of all different shapes and sizes. This one right here, Letitia, is about 100 kilometers across. But we have other smaller ones as well. And some, like one we're going to talk about in just a second, called Bennu, it's only half a kilometer across. Okay. So it just gives you a feeling for some of the objects that we'll be talking about today. Okay, so now I'm going to start talking about missions that we have to small bodies. And then again, I'm going to focus on ones where I happen to have some kind of personal involvement with it. And that's just because it's easier for me to talk about, but also because people have given me lots of cool animations, so you'll like to see them. So, okay, so we're going to talk about first about the OSIRIS-REx mission. The OSIRIS-REx mission has been a big success. It's mostly complete. Now we're just in the final stages of the process of writing up all the papers on the samples we brought back. But this mission was a sample return mission, and it went to this bottom. Okay, so if we go back in time, this is what we thought Bennu is. Almost all the information we had on this small asteroid called Bennu. Bennu's got an orbit, which you can see over here, which is not so different from the Earth. Okay, and that means that it's possible for a spacecraft to go out and visit it and get a sample and bring it back to the Earth, and within sort of the energy budget or the propellant budget of what you have for the spacecraft. But the problem was we didn't know much about Bennu. This is a radar image that we had for Bennu, and so we were able to put together a shape model. And so what it looked like, again, is we had a good size for it. We knew how fast it was spinning. Its density was just a little bit more than water. If water would be 1,000 kilograms per meters cubed. The bulk density is just a little bit higher than that. And so we thought that this body was going to be very porous. And because we understood something about its composition from its spectral properties, we knew this would be a very primitive material, something that hasn't been heated very much over its lifetime. But beyond that, we didn't know a lot. Okay, so we thought this would be a great object to go get a sample from, and we got a mission from NASA, and we went to go do this, and we're all very excited. Okay, so this is sort of where we're at. It's a sort of a quick version of what we knew beforehand. Okay, so this plot just a reminder to say that one of the reasons we wanted to go here is that this is a spectral fingerprint of what's going on in this asteroid. And what this shows is that this body has a lot of water that's tied up in silicates. It's what we call phyllosilicates, right? And just to sort of give you a feeling for what that means, there was a couple of years ago, Dan Durda, some of you may know Dan Durda. Okay, so Dan's in our office, and Dan did a really fun experiment for a television show. He took a piece of what's called a carbonaceous chondrite, which is what we thought Bennu was made of. And we have meteorites of this. And he put it in a test tube down here, and then he put a little top on it, and then he just took a blowtorch and he just kind of waved it by the test tube. And what happened is that when the inside the container got hot enough, all of a sudden, you're not even close to melting the glass or anything else, all of a sudden water just popped out of the rocks. You can see all the little water beads inside. Okay, that's what happens with phyllosilicates. They are filled with water, and that's very suggestive of where they may have formed. And we'll talk more about that.
How do you rule out adsorb water on the dirt before where it came from?
I think these were actually carbonaceous chondrite
But
samples.
you have to do it. You have to start with an evacuated test tube with no moisture in it, and then you do that. All he did was he drove off the adsorbed water that's on the very fine grain material, and it condensed. It's not from the dirt, from inside of the dirt.
What can I tell you?
Okay, it's great.
Sorry, you can go yell at Dan.
I will.
He did this for TV.
Hey, he's the one who's famous on TV for it.
Okay, I can't answer. Okay, so let's go forward. Okay, so here's what we're dealing with. So the mission's idea was this: is that we have this sample container, which is about the size of an air filter. If you've ever looked inside the engine of your car, it would gradually touch the surface of the asteroid. You would take nitrogen gas in canisters. You would have the gas be pushed through the air, through essentially the sample container into the dirt. The dirt would be pushed up inside the sample container, and it had this almost little rubber pieces that would blow out of the way so the sample can get in there, then the rubber would go back. So you remember those things they used to call roach motels? Like the roach goes in, but it can't get out. This is sort of the same thing, right? So you're gonna get the sample in the sample head. And then you put the sample head in the spacecraft, and then the spacecraft, the clamshell and the rest takes it back to the Earth. Okay. So that was the idea. So we had this great spacecraft, great mechanism. We're all excited, and we go out to Bennu, and of course Bennu looks a lot like it did in the radar, and so we thought, oh, this will be great. Okay, but I guess I would say this: our expectation at the time when we went out to Bennu is that it was because it was so porous. We really thought the surface might be very much like the moon, like filled with lots of dusty, dirty stuff that would be pretty easy to go into the sample head. But if you look carefully here, what you see is a lot of stones. Okay. Lots and lots of rocks, okay? And then here's a close-up of what that surface looks like. And this thing is all boulders, okay? Boulders as far as you go down. This is what we call a rubble pile asteroid. So, way to think about it is imagine you took a bunch of boulders and you dumped them off a truck. and you made a big pile. And imagine that you put that pile in space, so the only thing holding it together was the self-gravity of the boulders. That's Bennu. Okay. Our ideas were we were going to see lots of soil here that we could collect, but it turns out the solar wind is very good at driving off this material. Okay, and our mistake was that these boulders are just incredibly porous. Okay, they're really, really porous, and so that gave the illusion. Oh, okay. No, it gave the illusion that maybe we'd be having an easy time collecting things, but in fact, it looked like, oh my God, we might not be able to have a place to actually sample anything. Okay, so there's a lot of nervousness on the team. Okay, and so what we did is we had a meeting where we tried to go and find the best places on Bennu to go find a sample. Okay, and this animation's a little jerky, but I think I'll point out in a second. In the end, we found 4 possible places to go. And we gave them the names of different birds, osprey and kingfisher and the rest. Okay, I think this will pop up. But all of these places have problems because they all look like they have lots of boulders inside. They're almost all the regions where we've had a fresh crater on the surface. So finally, after lots of analysis, we decided the best place to go was this place on the upper left, which is called Nightingale. And so here's what the Nightingale site looks like as we sort of go in and look at it from sort of different angles. Okay. And you can see it's not the most glorious place for to send a spacecraft. You have this giant rock over here, big boulders over here, and somehow we're going to sample in the middle of this. You can see that's a little bouldery as well.
What's the scale?
I think this is about 10 meters across from here to here. Okay. So there was a lot of worry and angst that we weren't going to get a good sample, what happens, the spacecraft was going to go down and make a mistake and hit one of these rocks, and that would be the end of our billion-dollar mission. Okay, so, but what can you do? You have to persevere. So we went forward with this, and so this was the plan. So OSIRIS-REx was going to come in. This animation's a little slow. I might just have to fast forward through it, but yeah, it's jerking a little bit. Well, okay, so ultimately, what the spacecraft's going to come on, it's going to take a turn and then match course and speed with the asteroid's rotation itself. And then it's going to come down. I think the spot we're trying to reach is right here. And then it's going to do some last minute corrections, go do our sample. So it's going to gradually touch the surface, make a tag, and then immediately after the tag, it's going to get out of it. Right? It wants to get out of there fast to make sure there's no more damage to the spacecraft. If there's any dust or anything that comes out, we want to avoid that as well. Okay, so that's what we did. And so this is what it looked like. So I'll save you some of the drama. So we came in. This is the camera of the sample head coming in. You can see all the boulders and the rest. And then that moment that we touched the surface, it blew all the nitrogen in. But we found out a couple interesting things as well. It turns out Bennu is incredibly weak. And so when the spacecraft was coming down, when we put the sample head in, we kind of expected the ground to kind of push back a little bit, but in fact, we kept sinking in. The whole thing kept sinking in. So, I mean, some of you have done that. Have you ever gone to like a place where they have a lot of stones? You put your foot on it, and your foot just kind of goes all the way through the stone. That's kind of what happened here. Okay? And then we blew the nitrogen gas to put the stuff into the sample, but it turned out that material was so weak, we actually created a crater. Okay, so that's what you're looking at here. So the gas blows. And all of a sudden, you can see we left behind a huge hole. Okay, so this is what the site looked like before we grabbed the sample. And I'm going to show you afterwards so you can see the difference. So that's before, that's after, before, after. And just to give you a feeling for this, take a look at this spot right here. Okay, there's nothing there. And now look. Somehow, we blew a huge boulder all the way over here. Because again, there's not much gravity on Bennu, but also that the force of the nitrogen was actually quite a bit to blow things around. Okay, but so you can see we left behind a crater and the rest. But then the question is, did we get a sample? Okay, so this is what we saw almost soon after we had sort of pulled away from Bennu itself, and you can see there's all these particles flying around here. And the worry was that at least one rock may have been holding open one of sort of the rubber flaps. So if we put a sample inside the head, could it get out? And it might be leaking out. So as soon as they saw this, they decided they had to put the sample head into our vessel to protect it as quickly as possible. So that's what they did. So they put it to bed as fast as they could. And the thinking was at this point, we were going to do a test that had essentially spin the spacecraft with a sample head to see if we had any sample inside, but we couldn't do that because we were worried about leakage of material. So ultimately we put it back in, and then we closed the clamshell. And from there, we had to wait about 1.5 years to get the sample back and see if we actually had something. Okay, so go forward, jump ahead. So the spacecraft comes back to Earth on September 24th, 2023. Here's our PI, the PI of the mission, the principal investigator, Dante Loretta, out there looking at the sample in the desert in Utah, where they were able to collect it. Immediately after they got this, they wanted to get this into a protective container as soon as possible because they wanted to avoid any kind of atmospheric contamination. Because that's the goal of this mission, is that we have meteorites landing on the Earth, but then they get contaminated by our atmosphere, our water, everything else. And we wanted to see what would samples be like if they had no contamination whatsoever. And then what they did is they put the sample head into this vessel, which was filled with nitrogen gas. So ultimately it would be protected from the atmosphere, but then all the analysis had to be done with these little rubber glovey things, right? So, so imagine trying to do anything with rubber gloves on. That's what they had to do here. Okay, so that's what they did for several weeks and months. And when they finally opened up the vessel, so you could see everything. Here's the sample head over here, but you can see all this sort of grainy stuff that's around here. Okay, this is all particles from Bennu that were sort of didn't get inside the sample head, or they came out over time in the rest. So you can look at all this fine stuff here. Okay, so here I'm going to tell you a quick story about how you know you've chosen the right profession. Okay, so I look at this and I say, wow, what are you going to do with all that? I would just take a brush and kind of sweep it into a container, right, and use it all. But no, every one of these little particles has to be taken with the tweezers and cataloged and put into analysis so we know exactly what we're dealing with. So I talked to a friend of mine, Tim McCoy. He's the curator at the Smithsonian Institute of their meteorite collection. And I talked to him about this, and I said, oh, that must have been a horrible job. And he goes, no, that was like the best job I ever had. He loved it. So you know you've chosen the right profession is if you see this and you think that's going to be weeks of fun. Okay. So Tim is a true believer. Okay. So here's what the sample head looks like on the inside. This is what we got. We ended up getting about 120 grams of material, which is about twice as much as we told NASA we would get from the mission. So we fulfilled all our requirements in this. So a lot of the particles we got are fairly small. And again, think about this as sort of like, I don't have a good scale here, but think about this as sort of being like what the size of an air filter. So that gives you kind of a feeling for what you're looking at here and the rest. Okay, and so I'm not going to talk about some of the sample analysis because I want to talk about other things as well. I'll just say a few quick things. So the samples, turns out, are very rich in organic molecules. That's kind of what we thought we would hope we would get. So a lot of our analysis is going into what kind of organic molecules they are. And organic molecules are the building blocks for life. That's really interesting as well. We've determined, I think, from essentially the compositions of the materials and the fact they're water rich and where they come from, that the parent body for Bennu probably originally formed beyond Saturn. So it didn't form in the asteroid belt. It may have formed in another place and then been moved to the asteroid belt. And then from there, it went through a collision, and the collision created ultimately Bennu. Then Bennu came onto an orbit where we could reach it. Okay, and the samples are, again, also, as we already talked a little bit about, is that I seem to be very rich in essentially hydrated minerals. And that suggests that water was flowing through this body in the interior. In fact, we haven't found evidence in the samples, but also from the images of carbonates on the body itself. So this body probably, when it formed, had a lot of ice with it. The ice melted, and then the ice flowed around inside the body. Okay, or I said water flowed around inside the body and made some of these hydrated minerals that we have. So lots and lots of exciting stuff. Okay, so from there, I'm going to jump to Lucy. Okay, and talk about a second mission I'm involved with. Okay, so the OSIRIS-REx mission is almost done, but Lucy is got a lot of exciting places, or a lot of things to go in. Okay, so Lucy's mission is to go visit a population of asteroids that have never been visited before. They're called the Trojan asteroids, and Lucy was named after a set of fossils that were found in Ethiopia. Okay, that are sort of the precursors of humans. Okay, what were the humans like? And it was found by a researcher, Donald Johanson. I'll say a little bit more about him a little bit later. And the rest. And so it was thought, well, asteroids are fossils, and this is a fossil telling us about our history. And so missions to the Trojan asteroids are telling us about our history in a different way. So anyway, the mission was called Lucy for this fashion, and Lucy's actually been a great name. It's given us a chance to have a lot of great interactions, as I'll show you. Okay, so where we're going to is what, again, so the Trojan asteroids. So here's sort of a top view of the asteroid belt. Here's our planets we know, Earth and Mars. And here's the main asteroid belt. I've talked about that. The Trojan asteroids are in actually the same orbit as Jupiter. Okay, it's really crazy, right? They're in the same orbit as Jupiter. basically Jupiter's pulling on them, the sun is pulling about them, they're trying to go around the sun, and when you put all those the combination together, you find out that there are stable zones in Jupiter's orbits. They're called Lagrange points. So L4 is the population that leaves Jupiter, and L5 is the population that trails Jupiter. And for whatever reason, these guys have a lot of objects there. And I'll talk about some ways about how they might have been filled in just a little bit. Okay. So Lucy is a tour of Trojan asteroids, and we hope to have at least 5 Trojan encounters between 2027, so a little bit less than 2 years from now, all the way out to 2033. But some of those Trojans, it turns out, have satellites. So ultimately, we're going to get to visit 8 Trojan asteroids. And as part of this mission, we've actually had a chance to visit some main belt asteroids. I'll show you a little bit of that in just a little bit, okay? Because they've actually been lots of fun. Okay, so this is something that I just want to point out because we live in Colorado, is that you tend to think about missions, like who makes these missions and the rest. Lucy, in large part, is a Colorado mission, okay? A lot of the work has been done by Southwest Research Institute, where Bob and I are from, okay? So it's where our PI comes from. We're doing the payload management, the science implementation. We have a science operations center. A lot of the spacecraft design and construction, mission operations was done by Lockheed Martin, which is down in South Denver. And then United Launch Alliance, who launched our rocket, they actually have their headquarters in Denver as well. Okay. There's also Goddard was also involved, and they're out in Maryland. They're not part of Colorado, but everything else is a Colorado byproduct. So Colorado does a lot of interesting work in the planetary science field, and we work together to try to do cool things. Okay, so here's the spacecraft for Lucy. So this is sort of a fun little slide, okay, in the sense that over 500 people have worked to design and build and test Lucy. The spacecraft weighs about 3,300 pounds, so it's about as much as a rhinoceros, but about half of that weight is fuel or propellant. Okay, it's got about 2 miles of wire in it, and the spacecraft is built to withstand really, really hot and really, really cold temperatures. And if you're wondering about these solar panels, about how big they are, I have a really great reference. Okay, so this is how big they are. Okay. I'll show us. So you pop up. They're about as big as a TIE fighter, right? So it's about 24 feet across. So you can think about 24 feet, maybe, I'm going to guess it's maybe something like this to the wall. And these solar panels are effectively cloth. Okay. What we had to do is, if you're going this far from the sun, you need a big, big solar array to capture the sun's energy. But the problem is that big solar panels are usually really massive, and that works against you, right? So what they developed were solar panels that would sort of open up like a Chinese fan, like this, okay? And then they would be very lightweight, and once they're locked in position, it's almost like an umbrella, and they can be very rigid, and actually works really well in space because you don't have the wind and everything else, okay? Now, a problem we had is one of these solar panels didn't fully open, okay? And we've managed to we have managed to manage the problem, okay? And I think we're going to be okay for the mission, but this created lots of angst for our PI, Hal Levison, for at least a year after the mission was launched. Okay, so I'm not going to talk a lot about that unless people want to know more, but I don't know if I can really say a lot. Okay, so I mentioned that calling this mission Lucy had some interesting ramifications. So Lucy was called Lucy, the Lucy fossil, because that night when Donald Johanson and others went back to the campfire in Ethiopia, I think they turned on the radio and Lucy with the Sky with Diamonds was playing for the Beatles. Okay, and so Lucy has a connection to the Beatles. And so we thought, well, could our mission also have a connection to the Beatles? So it turns out we asked permission, and someone very special decided to send us something. Oh, is there sound for this?
Yeah, we were hearing it earlier. I don't know.
Oh, let's do that. Okay. I was hoping there would be sound for this. Basically, Ringo is telling us peace and love, and he's very excited about Lucy, and that John Lennon would love this. So, yeah. Sorry about that. We had sound earlier, but
Yeah, we did.
yeah, well, it can happen. Okay. So I'm gonna go long on time, but this is actually pretty fun. This is actually the launch of. I think I'll just start. This is the launch of Lucy, and even people that have seen lots of launches at the Cape thought this was one of the most beautiful launches they'd ever seen. And the reason is because we don't have sound for this either. So we're missing sound. Yeah. So are we just missing sound on everything now?
What about John?
The reason I ask is that I have a couple of things that will require sound. But watch Lucy as she tries to figure this out. Watch it go into this cloud bank. So we have plenty of volume. It's just I wonder if somehow
You probably have the zoomers muted, right? So maybe we.
So I think when you shared screen, there is a way to share the sound, especially with Zoom, but also on the screen. So it may be in that setting.
Okay.
so.
Anyway.
Anyway.
Right.
Watch what happens as Lucy goes through these clouds as they're doing this. And this is really the fun part, right? So I got to see this live and it was pretty good. So what? It's gonna get even better right there. Oh, it's now it froze. Okay, so essentially what happened is it looked like angels coming out of the clouds. It's very, very exciting. Okay, so the Lucy launch was great, and then right afterwards we had the solar panel issue. So you go from like you go from the ecstasy to the agony, that sort of thing. So, but okay. Oops, and now I think I can't go forward.
Oh, right. Give me 1 second. I'm gonna see if I can.
Okay, it's not crucial. I have sound. I just thought I'd ask about it.
Oh,
It sure would be nice.
So what time of night?
Dewey, you probably have to unshare and then look for the sound setting and then reshare.
Okay, I will try that.
While he's doing that, I can take some questions. Are there any questions so far?
What time of night is this?
This was, I think this was about 5 a.m. Yeah, because we had, I remember, I brought some of my family with, and we had to get up, I think, and get the buses about 2 a.m. and get to the site by the gate, and then but you're okay with this because you're going to get to see this, right? So it's very exciting. So we all got like 4 hours of sleep, that sort of thing. So, some people didn't sleep at all, but it was worth it.
Is Lucy a sample return mission?
No, Lucy is only going to do flybys. So it's going to do a first reconnaissance of all the bodies. And I'll talk about that in a second. I can't forward at the moment. So
what's the time delay to then
the time delay to
the asteroid where you got the sample?
Oh, what's the time delay between like going to Bennu and then coming back?
What I'm saying is that had to be autonomous when it was.
Absolutely. Yeah. I think I don't remember what the time delay was off. It was long enough that you're right. It absolutely had to be autonomous. There was no way to do it in real time, and that's what was scary. Is because the engineers had to basically set up an automated system to be able to go in and be able to grab the samples and back. But they had to come up with a tracking system because of all the rocks close by to make sure that they would actually know where the spacecraft was at all. Solar panels and the rest wouldn't run into some of the big rocks that are close. So let's just go.
All right. I should have sound, and I want to back you up to Ringo.
Okay, you guys want to see Ringo? All right. Well, let's try it. Oh. Okay. And okay. We'll try to get it later on. That's right.
Yeah.
A little noisy, but
Okay.
I'm so
Okay,
excited.
sorry about that. Okay. So this is a little bit of the sciencey part of it, but I think it's always fun to talk about, well, how do we get Trojans in the first place? Because some of the reasons we're going to the Trojan asteroids has to do with some of the things I want to show you here. Okay. So to tell you about how we get Trojans, I have to sort of again go back in time. Okay, so I was a young, eager grad student back in the early 1990s or so. And one of the things we were trying to do with my advisor is try to figure out planet formation. How does planet formation work? But back at this time, we didn't know about any extrasolar planets. We didn't know very much. All we really knew is in the outer solar system, we had these 4 giant planets and Pluto. Okay. But the weird thing about Pluto is that Pluto had a really weird orbit. Okay. Pluto is actually in an orbit where while it crosses the orbit of Neptune, it can never hit Neptune. The reason is it's in what's called a resonance. So Pluto goes around the sun twice for every time Neptune goes around 3 times. So we call that a 2 to 3 resonance. And so the question is, if these are the only worlds we have, why is Pluto in a resonance with Neptune? And also you can see Pluto's orbit is really inclined compared to the sort of the plane of the solar system. It's way, way out of the plane. How did they get that? This was in a long-term mystery, and no one had a good answer. Okay, so we were trying to figure this out, but we didn't have a good answer either. Okay, eventually, an answer became more apparent as we went along. Renu Malhotra, this was sort of one of her big works to put her on the map as well. But also, we started to find things. what we found is that Pluto is not a single object out there. There's actually a lot of objects out near Pluto. Okay, we call this the Kuiper Belt. And so again, remember the plots I was showing before. This is semi-major axis, so this is sort of distance from the sun. And over here we have a parameter called eccentricity. So eccentricity is imagine you have a hula hoop. Okay, a hula hoop is a circle, right? So it has no elongation. So we would call that 0 on this plot. Okay, but if you take a hula hoop and you start to bend it and you make it more and more elongated, this eccentricity goes up. So this is just telling you about the orbits of things. So what we found is that that Pluto is not alone. There are a lot of objects in orbit, or it's in resonance with Neptune. Okay, and then the question is, how do they get there? So I'm going to show you a simulation right now that explains why. So Neptune, this is this blue dot here, is going to go out. And it's actually going to encounter a massive population of objects, what I'm going to call the primordial Kuiper Belt. Okay? When it does that, it's actually, because it's seeing all these objects, it's going to take them, it's going to grab them, it's going to do an encounter with them, it's going to throw some objects outward, it's going to throw some objects inward, and the net result is going to cause this object to migrate upward. Okay, so looks like this. Okay? And so dynamically, what's happening is that as this object is migrating out, there are certain objects that can get picked up in this resonance and actually get caught there. Okay, so that's why we think Pluto is in a special case. Pluto is just one object of many that happen to be out there. But what we think in order for this to work is this population used to have to be much, much larger. Okay, so we went from a population which today doesn't have much material out there, but in the past that maybe had to be 1,000 times larger. So while today we have one Pluto, back in the past we may have had thousands of Plutos. Okay, and this population was probably several Earth masses of material.
Did you move Neptune, or does it get dragged by the population?
I'll show more about that. We'll come back to that question in just a second.
Okay.
Okay. So here's the issue, though. Okay, so if Neptune migrated, if Neptune moved, then the giant planets didn't form where we see them. The giant planets also had to move. Okay, and that sets up a whole interesting scenario of how our solar system evolved. Okay, so what we're thinking now is that our solar system formed in a very different configuration. Okay, so Jupiter forms pretty close to where it is today, but Saturn, Uranus, and Neptune may have formed closer to the sun. And then beyond that, you have this population, which is maybe several tens of Earth masses, all in small bodies like Pluto, but also 100-kilometer bodies and everything else. Okay, so that's why we think the solar system may have formed. But in the end, it has to get to this configuration. This is what we see today. And this has to go from tens of Earth masses down to a population which maybe has a Mars mass or so. Okay, so how does this do this? Okay, well, this is where the head of our mission, Hal Levison, was a big person involved with this. They developed something while he was on sabbatical in Nice, France. So they call it the Nice model. Okay, and they also call it the Nice model because it's a nice model. Right? So it's like, although don't go to Google and type in nice model, you'll get something different. Okay, so on the left, this is what you're looking at. So this is a system of planets. And you'll see that this population is gradually losing some objects. Okay, dynamically it's losing some objects, and that's causing Neptune to migrate ever so slightly. And when it migrates enough, the system goes unstable. Okay, so Neptune migrates through the population. It sends a lot of this mass into the other giant planets. They all begin to move around. They begin to have encounters with one another. The whole system goes crazy. Okay? But what's really funny about this system, though, is that this model does a great job of reproducing the orbits we have for the giant planets and where they are in semi-major axis and where they are in eccentricity, and also how inclined they are to the plane of the solar system and inclination. It's the only model we have that really reproduces all this right now. So despite all this craziness, this model really seems to work. And I've spent probably the last, I would say, 20 years beating on different parts of this model. And every time we think we come up with a fatal flaw, we investigate it, and it actually ends up not being a fatal flaw, but it teaches us something about the solar system. It's amazing. Okay, so I said I was going to explain how we get Trojans. So this is how we think it might work. Okay, so here's what we think the system might have actually been like. So the previous system I showed you only had 4 giant planets. But now imagine that very long ago in the early part of the talk, I said, maybe we have an extra Neptune. Okay, let's imagine that's true. It turns out those systems work much better than 4-planet systems. So in this case, what's happening is that we're actually losing a Neptune. Neptune is going down and encountering Jupiter, and then Jupiter is throwing that guy out of the solar system. Okay, but in the process of encountering Neptune, what it's doing is it's causing Neptune to jump. These encounters are causing Jupiter to jump just a little bit. Okay, so imagine right now Jupiter's surrounded by Kuiper Belt objects, like it's over here. Okay, Jupiter's jumping, that's getting encountered by a Neptune that's going to get thrown away. And what it does is it moves some of its Lagrange points, almost like throwing a net on top of the Kuiper Belt objects. So the objects there at the right place at the right time can be captured. Okay? What we estimate is there's about a 1 in a million chance of an object getting caught in this. But there's so many objects coming out of this population that 1 in a million is about right to give us the Trojans that we see today. Okay? So if this is right, the Trojan asteroids we have started their lives beyond Neptune, and they're actually sort of transplanted Kuiper Belt objects. So that's fun. Okay. So that's your dynamics lesson for today. Now we're going to go on more dynamics. All right. So this is the trajectory we have for Lucy itself. So you can see it just went out and passed a main belt asteroid called Donald Johanson. But ultimately, it's going to come out here and encounter 4 different Trojans. Okay. And we're going to do this over a series of months, starting I think in July of 2027 or so. Okay. So we have 4 encounters. Then it's going to come back and encounter the Earth once more. And then back out in 2032, we're going to encounter our last Trojans and the other Lagrange point, the L5 moon. And here we're going to do Patroclus and Menenius. Okay. So it's got a great orbit. Here's sort of an artist's rendition of what these guys look like. And we tried to pick these objects sort of to represent the various diversity we have for the compositions of the Trojans, but also a little bit of what they're doing dynamically. So there's a couple of interesting things here. Okay, so first of all, this object right here, Euripides, has a little satellite. It's called Cata. Okay? That's why this little guy is over here. This is actually something we found after launch using the Hubble Space Telescope. So that's an image from the Hubble Space Telescope. So it's got a little satellite. And we think what happened is that this body Euripides has got an asteroid family with it. So it probably experienced a giant collision. The giant collision threw fragments away. But some of these fragments didn't escape and actually went into orbit around the body. Okay? That's how we think we might have gotten a small satellite as a byproduct of a big collision. So Euripides is going to tell us about what a Trojan looks like after you blast it off the surface and you left with things on the inside. Okay. We also have these 2 guys. These 2 guys are both about 100 kilometers in size, Patroclus and Menenius. And that's a representation of what their orbit is like. So if you remember again, at the very, very beginning of the talk, I was showing you how planetesimals form. And I was having all these small bodies collapse down. It turns out a very common outcome is to have, after all that collapsed down, is you end up with 2 bodies that are orbiting one another, just like this. So these bodies might tell us about the original planetesimal formation process and what are some of the byproducts of that, because they seem like they've been unaffected by anything else since that time. So they've been some collisions, but it hasn't really fundamentally changed them in fashion. So that could be fun. Okay. So I'm taking a long time on this, but it's fun. We're going to go through and we're going to talk about Dinkinesh. Okay. So this is some of the results that we have so far for our spacecraft. So this is what happened. So we launched Lucy, and then we had this Swiss postdoc named Raphael Marshall, great postdoc, and he decided to sort of take a look to say, okay, is it possible that our spacecraft Lucy is going to go by anything in the asteroid belt beyond what we've already detected? And it turns out he ran all the numbers that there was one small asteroid that Lucy was going to fly so close to, we could actually do sort of a whole encounter with it. So we thought, great, we get an encounter for free, let's do it. So this is with an asteroid we call Dinkinesh. Dinkinesh, I think, means you are wonderful in the Ethiopian language, which is nice. Without people would like that. Okay. And so this is what it looked like when our spacecraft saw Dinkinesh. Okay. So Dinkinesh is about a 700-meter body. Okay. What you'll notice, it's got this little thing over here flying around. Okay. This is something we didn't know. We actually knew nothing about this body until we encountered it. And you'll notice it's got a very special configuration there. And I'll show a close-up of this in just a second. Okay. But when we saw this, this is what real life science is like. We all freaked out. Here I am over here. We're all screaming and yelling and everything else. But of course, a couple of our people, like Mark Bowie and Josh Emery, it's like they've seen it all before. It's fine. We don't care. But we were excited. The reason we're excited is that there's a couple of things here. So this is a scale bar, 1 kilometer. So this is Dinkinesh. Dinkinesh looks a lot like Bennu, doesn't it? I'm going to come back to why that is. But it looks a little bit like that. But this is a contact binary. This is a satellite that's a contact binary. We've never seen this before. We think these 2 are actually connected here. You just can't see it because of the shadow. But the question is, how do you make something like that? And why does that look like a top? These are all interesting questions. So we call this satellite Selem. And Selem is essentially the baby of Lucy in the mythology, the whole thing. So, okay. So this just gives you a sense of scale of here's the Eiffel Tower, here's the Empire State Building, the Colosseum. That's how big Dinkinesh is. That's how big Salem is. So you can see that, in the scale of things, they're big, but they're not that big. Okay, and here's what sort of Dinkinesh looks like from both sides. You can see it's got some really interesting shapes, but again, it's got kind of a top-like shape. And so the question is, why do these guys look like tops? Why did Bennu look like tops? Turns out, if we look through the small body populations, a lot of guys look this way. Why? I think we have an answer. Okay, so what I'm going to show you is this. This is an animation put together by Harrison and Bruce, who's on our Lucy team. So imagine for the moment that there's a process that can spin asteroids up. Turns out this is something that happens from sunlight. They can absorb sunlight, they heat up, and then they re-radiate the energy. In the process of doing that, they can actually change how fast they spin. Okay, so imagine you're spinning asteroids up by this effect. We call it the Yorp effect. And what you can do is you can spin up so fast that if you're a rubble pile, you can shed mass. And you can create sort of a little debris disk around you. Okay, so you have things that are coming off of here. Some of them go back into accrete, and that kind of gives you kind of a waistband around these bodies that basically kind of look like a little bit like a top. But also you have all these other fragments, and some of these clumps could merge together to give you a satellite. And in some special cases, you might have two clumps come together that merge so gently that they actually retain and continue to be a contact binary. We think that's maybe what happened here. It could be that Salem formed in a single event, or it could be there have been multiple events like this, and so you make one satellite, and you wait a while, and then you make another satellite, and they come together. That's how we think we make this. And this is also because of the spin-up mechanism, and this is why a lot of asteroids have this kind of shape. So it's pretty fun. Okay. So there's one other thing I wanted to show here on Dinkinesh, and I think we'll leave Dinkinesh for now. If you notice this, there seems to be almost like a sort of like a trough or some kind of contour here on these different images. Okay, and the question is, what's causing that trough? Okay, well, we think what's going on is the same kind of thing. So imagine you're taking Dinkinesh and you're spinning it up, and just like a figure skater pulls out her arms like this, we think that's what's happening here. Is that this whole section may have been moved out, okay, because of the spin up of the body. So it took a whole coherent block and pushed it out further just from centrifugal forces. Okay, so again, it shows you that that the spin up mechanism called Yorp does a lot of interesting things as a geologic process on these bodies. Okay, I'm worried about how am I doing time wise? I'm a little worried about time. Okay. So we're going to talk very briefly about Donald Johanson, because Donald Johanson is still alive. Okay, so at our last, we had another encounter with a main belt asteroid that we named that asteroid after Donald Johanson. Here he is. Okay, so we named the asteroid Donald Johanson, but the real Donald Johanson actually came to the encounter. One of the great things about calling the mission Lucy is that Donald Johanson has been loving it, and he's been enjoying interacting with the team. He's come and given us all these great science talks about the history of humanity, all those sorts of things. And so here he is. Okay, and just since we like celebrities, you might recognize this guy. This is Brian May, okay, from the rock group Queen. Brian May is a big space fan. He's got a PhD himself, and he's an excellent at taking images and turning them into sort of three-dimensional visualizations that you can look at features and the rest. And so he comes to the team. He's like a super nice guy. Everyone loves him. He can come and hang out all the time he wants. I think he takes his private plane to come and be on the mission things. But it's lots of fun. So we can see Brian's doing his thing over here and the rest. Donald Johanson is here. So I'm a little starstruck. We get to have some fun with this. Okay, here is what Dinkinesh. This is what Donald Johanson looks like. It's a very elongated asteroid. It's about twice as long as it is wide, and it seems to be almost like a contact binary. And it's got two different components put together. You can see all the craters and the rest you might expect. But one of the interesting things that we're still trying to figure out is this neck. Okay, this neck doesn't have very many craters on it. That suggests it's young. And the thinking is that this probably produced in some fashion by landslides, as this object has changed spin over time by the same Yorp effect. Okay, but we're still trying to figure out the exact reason for this. But what's really interesting is it turns out a lot of asteroids have a very similar feature. Even some comets have a feature like this. So it seems again to be a common process that's happening to bodies that are sort of elongated across the solar system, which is fun. Okay, so Hal always likes to put this in. I love Lucy. I love Lucy too. So we'll put that in. Okay, so now we're gonna go like, just like in a movie, usually you start with the coming attractions. Now we're gonna have more of the coming attractions, right? So we're gonna end with this. Okay, so I want to talk about Psyche. Okay, so the Psyche mission, we have a tagline, and that is called "A Journey to a Metal World." Okay, and so ultimately we're gonna try to go visit something that's not just made of rock, not just made of iron, but is predominantly made of iron. Okay, but when I was in high school, if someone said you want to take a journey to a metal world, I would have thought a little something different. So in high school, I would have thought it more like this. Better than so yeah, this is the metal world I was familiar with, but okay. So, and we still actually have a lot of fun on the mission with this. We put umlauts in a lot of our things, that sort of thing. So, okay, but ultimately, all right, the issue is this: is that what's the rationale behind why was this funny? Why was NASA interested? Well, I think as scientists or geologists, we'd all like to understand the interior of the Earth and the Earth's core. That would tell us something about how the Earth evolved, tell us something about planet formation, all these sorts of things. But going to the core of the Earth is simply not possible today. Okay, we learn a lot from seismology. We learn a lot from samples that have come up from the interior, maybe from the mantle and the rest about the Earth. But again, like there's no way to journey there. So ultimately, we'd like to know much more about the core. It's hard to get to. Now, there is a way we could get to the core, but it has a certain cost to it. Okay, so one way to visit the core would be this, right? So, okay. Yeah, so if we could fund a Death Star, and we could do the following. We pull up the Earth. So that would be a great science ways. In fact, if we might even get some money from the Rebel Alliance to do something like this. But okay, but ultimately the question is, it's very hard to get to the center of a large planet. But it turns out what I just showed you here, there's a reason I showed you. It's funny, right? But it's also there's got some truth behind it, right? So early on in solar system history, very big things slammed into one another. Okay, some of these bodies were often differentiated, so they had an iron core. Sometimes that core was molten. Then the collision, though, will in some cases take bodies and really rip them from end to end. Okay, and you can see here of the things that come off of here. The red represents the core material. Some bodies are very rich in metals. They might have some silicates from the mantle or the crust, but they can be very, very metal rich. We think Psyche might have been formed from some of these events. So Psyche may be a metal object or a largely metal object because of what we call these hit and run collisions. Okay, so this is one of the reasons we want to investigate. Okay, so our body Psyche is about 200 kilometers across. And for reference, here's what we have for Los Angeles to San Diego. If you like California, if you like Arizona, your Flagstaff and Phoenix or so. So it gives you sort of a feeling for how big 200 kilometers is. Here's what it looks like in reality. If we use adaptive optics on ground-based telescopes, you can get sort of a feeling for the shape of Psyche. So it's not a sphere. It's got an unusual appearance, it's irregular, and it actually has some albedo features on the surface as well, which tell us that maybe it's had some cratering events, and maybe it's just even some different compositions on the surface. We're going to find out when we get there. Okay, so this is a animation that was put together by someone who was associated with the team of what it might be like to visit an iron-rich world. Okay, you can tell it's very early because it has different solar panels than what we have right now. And this is mostly for fun, but it's still sort of evocative, right? That's just why I like it. So the question is this: if you go to a world that's largely made of iron, we've never visited a world like that. So what would you expect? Like, what would craters be like on on a world with lots of iron? What would cracks or flaws or grooves be like? Why would they form? Could you have volcanism or some kind of weird heating? What would happen on a world like this? No one knows. And so while these images are kind of crazy, I don't think it's going to actually look like this. We don't know if it's right or wrong until we get there. And so this is hopefully some of the fun. Is a sort of a brand new way to think about visiting a very different. It's like Star Trek, right? You're visiting a world that no one's ever visited before, and it might be out of your experience. So who knows what you learned from that? So that's one of the reasons we want to go. So you can see this flying around again. You have all sorts of interesting colors of the rest, which I think is sort of representative of the iron. You have this sort of giant crater thing up here, giant stalagmites, stalactites, stalagmites, whatever you want to call it. So, we'll see. I don't think it's going to look like this, but it's fun to think about. Okay. So this is what our plan is that we're going to fly out we just launched in 2023. We're going to get there in 2029. And then we're going to, over a period of many months, we're going to start off with a very distant orbit and then kind of gradually work our way closer and closer until we finally have a very, very close orbit. And then from that, we're going to try to learn about the composition using a gamma ray spectrometer. We're going to have imagers aboard. We have a magnetometer, so we're going to try to see if this body had a magnetic field, or if it has a magnetic field. And if it did, that might also tell us how it's solidified. And that would tell us something possibly about the hit and run event. So there's all sorts of things we're going to be able to learn from this. So here's what the actual spacecraft looks like. Here's all the partners that we have represented. And again, it's going to arrive in 2029. So we have a few more years to go, but we're hopeful it's going to be fun. Okay, and so I'm going to finish. I know I'm going long, but I'm just going to finish with Surveyor. So everything I've done so far is talking about visits to individual worlds or like multiple worlds, that sort of thing. But there's a different reason we also are interested in asteroids, and that asteroids have the potential to hit the Earth. And if one hits the Earth, it has a possible, people could lose lives. There's all sorts of things that can happen. So NASA's been very interested in this over time. And so what they want to do is see, can we come up with a mission that can find hazardous asteroids? Okay. So this is just sort of a reminder. I showed this at the beginning of the talk, but it's a nice animation, so I'm going to show it again. Here's the asteroid belt. Those aren't crossing the Earth's orbit, so they're not a threat. There's a lot of objects in here that do cross the Earth's orbit. They're coming from the asteroid belt and they're replenished all the time. So, but a lot of those bodies we haven't found yet. We found some of the largest ones, but a lot of the smaller ones are still very hazardous, haven't been identified yet. So we'd like to find them. Okay. So right now, what we're doing in terms of finding asteroids is we have a couple of surveys that scan the night sky all the time, looking for threatening bodies. The two big ones right now are the Catalina Sky Survey, which is working out of Arizona, and then we have the Pan-STARRS telescope, which is working out of Hawaii. Okay, and they're actually really good at what they do, and they found a lot of objects. But there's just a limit to what they can do over a given time, given that they're on the Earth. And there are like certain apertures and certain, there's certain abilities and what limiting magnitudes they have. So this is what has happened over time. So again, when I came in the field back here, we had almost no asteroids. This was back in the days of Gene Shoemaker and all the rest. It was almost barnstorming in terms of what they were doing in finding objects. But since then, the survey's done really remarkably well. We think we found almost all of the kilometer-sized guys. There are about 1,000. There's about 1,000 of them or so. But then about the 140-meter guys, which we think could still cause a sizable amount of damage, we think we've only found about half the population. So we have a lot more to go. Okay. So this is just to sort of set up why are we doing Surveyor the way we are. It's an infrared telescope, so it's going to look for asteroids in the infrared. And the question is like, why the infrared? Why do you want to do that? Well, there's a couple of reasons. So this just helps to set that up. So if you're looking at asteroids in visible light, okay, what you can see is if you have an asteroid that's made out of chalk, which is really bright, it gives off a lot of light. But the same brightness would come from an asteroid that would be much, much larger, but it's the same thing as charcoal. Okay. But if you're looking at the infrared doesn't care about like what your surface properties are. It just cares about what the heat you're getting off and how hot you get from the sun, and then how much heat is coming off. As you can see here, you can get lots of different brightnesses depending on the size of things. And so being dark doesn't prevent you from being found. It actually, in some ways, just all we care about is how big you are. Okay. So, and then also here's another way to look at it. If you made all these objects the different compositions, okay, but they're all the same size, they would all give off the same brightness in the infrared, as opposed to what you see elsewhere. So essentially what we have with an infrared telescope is you're not biased by composition. You really just care about like size. Size is the only thing that really matters in terms of finding things. Okay, so here's your fun audience participation thing. There are asteroids hidden in here, and your job is to find them, okay? And then I'm going to give you, it'll become easier and easier as I go along, but this also demonstrates some of the things of how this procedure is going to happen. One of the things that's really nice about the infrared is that the background population you're looking at is much easier to deal with than in the visible light. If you've ever tried to look in the middle of like let's say, look at the night sky and you're looking through the Milky Way and you're trying to find small objects moving, it's really, really hard. And the infrared is much easier. Okay. So here's the field of view that we have for Surveyor. It's going to cover the whole night sky, but our given field of view is about 7 degrees by about 1.7 degrees or so. Okay. Okay. Here's some of the things that you can see in the night sky. Here's planetary nebula. Here's galaxies. Here's a galactic cluster. There's I think some dust over there. And then here's some artifacts and the rest. Okay. So all these things we can identify. And ultimately the question is, okay, we follow that, but where are the asteroids? Well, once you sort of identify all the background objects, you can remove them. So we're going to do that. So, oh, sorry, I was going to say that. Yeah, there's actually if you look really carefully here, there's a little bit of asteroids here, and you can see the movement because there's several different images that have been added together here to see the movement. That's hard to see here, but if you know where all the background is, you can remove the background. There, that makes it much easier. Okay, and then you can also brighten things up and enhance things. Okay, so now all of a sudden you can see all these different asteroids that have been collected by adding together all these different images. Okay, and so here, and some of these are cosmic rays and other things, and the rest. But ultimately, here's all the different bodies you can see in the infrared by using this kind of image. And so this is what NEO Surveyor is going to do.
Okay.
So, and this object is also an asteroid, but it's got this wide separation because it's passing it's passing very close to the Earth, so it's crossing the sky very quickly. So ideally, we can find those as well. There's that. Okay. So that's an object they call a potentially hazardous object because it's so close to the Earth and it's moving so fast. So it's potentially could hit the Earth. Okay, so here's what our survey is going to look like. It's going to last. Our survey is nominally set up to last about 5 years. We hope to launch a little bit less than 2 years from now in 2027, and it's going to scan the sky. And over time, over 5 years, we think we'll be able to find about 90% of all the objects that are larger than 140 kilometers. We'll find a lot of the smaller stuff too, and we also think we'll clean up all the bigger objects. We should be able to find almost everything that was possible to find within the timescale of that survey, provided these objects don't hang around on the opposite side of the sun, so we can't find them. Okay, so it's about a meter. So the telescope's about this order of about a meter or so. It's going to be in. I think we're putting it in L1, and it'll sit there and scan for quite some time. Okay. I think at that point I'm going to stop. There's one more mission I could talk about. I'm involved with. This is I'll just say it's real fast. Okay. I'm a completist. I like to do this. I'm involved with one more mission. This is actually being led by the United Arab Emirates. This is they've decided that they want to have an asteroid mission as well. So they have a mission to the asteroid belt, and it's called the EMA mission, the Emirates mission to the asteroid belt. It also looks a lot like Lucy. Okay, turns out these solar panels are really handy for lots of different spacecraft. Okay, the Emirates are doing a mission because several years ago they decided it was really important to get their people more interested in science and engineering. Right now in the United Arab Emirates, when I talk to the people there, they have a lot of people are going into business degrees and everything else, but they want to prepare for the day when there's no more oil in the region. Right now, they don't have any oil in the United Arab Emirates, but they do a lot of business with all the people that do. Okay, but still, they'd like to have other fields be done in their field. And so they were trying to figure out how can they inspire their people to do this. And they said, well, let's have a mission that goes to Mars, and let's get our people involved with it. So this mission was called the Hope mission. It was actually very successful. It's still in orbit around Mars. And they liked it so much, they talked to the University of Colorado, which built the Hope spacecraft, and said, we'd like to do another one. And they said, well, we need a mission. How about we go to the asteroids? They said, great. Okay. And then, not long after they did this, I got a call from some friends of mine over at CU and said, would you like to be involved with an asteroid mission? And I'm like, yes. So, okay. So, you don't have to ask me. Asteroid missions don't grow on trees. I'm happy to be involved with it. So I've been able to, I've been involved in this mission. It's been great to work with the Emiratis. The Emiratis, it turns out a lot of the people on the mission are women, because it's a strange thing about this, right? A lot of the men go off overseas to go to school, okay? And the women stay behind. So the women go to university in the United Arab Emirates, but a lot of them don't go into business. They actually are much more interested in taking on engineering and science. And so we've had a lot of great interactions with them, and a lot of them are on our team. Because the Emirati women are very interested in, basically nerds are the same everywhere, and like they're really interested. They're very interested in asteroids and Mars and everything else. Okay, so this is a sort of an artist rendition of the bodies we're going to go visit, and I'm not going to go through all of them because it would take too long to say everything. I'll just say a few highlights on some of these guys. Right, so this is a picture of the asteroid belt in semi-major axis and in inclination. The stars are the guys we're going to. So I'll just give you a few highlights. So our main object we're going to visit is this one called Gestation. It's almost 50 kilometers across, and this object has a spectra which almost makes it look like a Kuiper belt object, and no one understands why that should be. Okay, so we're actually going to ultimately rendezvous with this asteroid, and then we're actually send a little lander down to it. Okay? So once we decided that's our main target, then the question is, can we visit other asteroids en route to going to Gestation? And so we had to come up with a list of asteroids. And so what we've done is all these other stars you see here are bodies we're going to visit. A lot of them are associated with all these red guys. These are what we call asteroid families. So there are so basically a big asteroid collision happened in the past, and some of the guys we're going to visit are fragments from those giant asteroid collisions. So we're going to visit Chimera, which is the largest remnant of an asteroid family. We're going to visit this world over here, which is part of the Eos family, and then we're going to go to several others. Okay? And then some of these objects are most of these objects are water rich and carbonaceous, but a few are not. And then some of them also have interesting problems. Like here's one in a family called Baptistina called rock ox, which may actually be a combination of carbonaceous material and non-carbonaceous material that was somehow created in a collision. We'll find out if that's true. So I think that's the end of my talk. So thank you for indulging me and letting me talk about everything I wanted to talk about.
All right, I think maybe we'll start with questions from the live audience here. And then after that, we'll switch over to the Zoomers. But I do have one quick question for John Williams. Did I understand your text that people on Zoom were able to hear the sound?
That is true. You shared the sound on Zoom. So not sure what's going on with the sound there in the hall.
What we could always do is that after we're done with the Zoom session, we could probably just put on, if they want to hear the Ringo thing, we could put on the Ringo.
Absolutely.
Absolutely. We'll do that, and the Zoomers have already heard it, so that'll be okay.
Yeah.
So,
Yeah, I was very pleased to see that. Okay, so any questions here?
yeah.
Why 140 kilometers?
Yeah, it's a complicated explanation. So I was involved with a study back in the 2000s. And what we did is we took all the different asteroids that we thought were out there, and then we combined how much each one would possibly produce in terms of damage to the Earth and loss of life. So it's almost like doing like a life insurance thing. Like this asteroid has a chance of killing this many people. This asteroid has a chance of killing this many people. And we put that all together and we said, what would it take to get rid of 90% of the remaining hazard? And it turned out the magic size was 140 meters. So the 140 meters gets rid of 90% of the remaining hazard, according to the study we did back then. But yeah, no, everybody wants to know, well, why 140? And we have to like, so that's why we decided to do that. Yeah.
First of all, awesome graphics, thank you.
Thank you.
And second of all, question, is OSIRIS-REx still going to visit Apophos when it comes back?
Yes, I didn't. There's too much to talk about. Yeah. So there's an asteroid called Apophos, which in 2029 is going to pass about 6 Earth radii from the Earth. Okay, it's very exciting. I think it's a naked eye object. I'm pretty sure it's a naked eye object. I think you're going to be able to see that. And you guys with telescopes, you're going to be in great shape, right? So OSIRIS-REx is now it's done its nominal mission. But now it has the opportunity to fly out and go visit this asteroid. And so they renamed the mission OSIRIS-APEX. Okay. Now, when this gets into the whole NASA politics thing, it looked like there was a chance they might be killing off all of the extended missions, including OSIRIS-APEX. But recently I was told, this was announced publicly, that NASA has decided to let that mission go forward. So OSIRIS-APEX will be going to Apophos. So that's good. Yeah.
So with the EMA, the flybys until you get to Just Bishop are very fast. I mean, we're going by like a bullet, and you have a very short amount of time to actually image it there.
That's right.
With Lucy, your apoapsis is so high. Do you have longer hang time around these flybys that you're doing, or is it also kind of a bullet and you better be on them?
It's all gonna be fast. I mean, you try to have is we're going to them close to aphelion, so we're trying to like lower the velocities as much as possible. But in the end, they're flybys, so we'll do as best we can with the flybys. But that's the only way we can visit sort of a diversity of objects. Right. The alternative is to do a rendezvous, but if you want to do a rendezvous with a Trojan, first of all, it's really, really hard. But really, you only get to do one object, and that's it, because you just don't have the propellant to go anywhere else and do anything else. So, yeah, it's a tough one. It's basically flybys versus rendezvous. That's it.
Right.
Yeah. Yeah.
Hyperbelt objects, can they explain the weird tilt that Neptune has?
Well, it's a great question. In a sense, yes. Well, let me take a step back. The thinking is that the weird tilt that Neptune has was produced early in solar system times when you were building the planets, Neptune may have been hit by an Earth mass object. And so the Earth mass object tilted it over. Okay. And so the thinking is that if Neptune got hit by something that large, there may have been many large objects like that in early solar system times. Now, most of them were probably ejected, but it's possible, so this is something that some of those objects, at this time, you may have had enough of these objects that that some of them, when they were kicked out, may have actually encountered a passing star because we were probably in a star cluster at that time. Some people argue that things like this may explain this proposed Planet 9. That Planet 9 may be an object that was formed, kicked out, and then a passing star circularized its orbit enough that way it's in orbit around the Earth. That's still in orbit around the sun. We just haven't found it yet. We'll see if that's right. I'm hopeful, but I don't know. I have friends in this debate and they all fight. So we'll see what they do. Yeah.
Is the asteroid though, could that be a potential planet that would form in billions of years time? Or is that finished? Or is that still happening?
The bodies are so excited right now. Dynamically, they're so excited that when they hit each other, they actually they collide and they go boom rather than accrete. In order to really form into a planet, they would have to have very, very low velocities with respect to one another, and they don't have that. Right. So at the moment they're not. Yeah, they can't form into anything bigger. Right. But you remember the animation I showed of material sort of leaking off of Dinkinesh and how it forms it. That's the kind of velocities you need for things to form. Okay. So things can form, but it's probably in a different context. Okay.
All right, so no more questions here. How about you Zoomers out there? You'll have to unmute yourself and ask.
I have a question.
Fire away.
Can you hear me?
Yes.
Yes, Linda, go ahead.
Given the amount of space debris and the number of asteroids out there, how do you design the equipment not to be affected?
Are you worried about getting hit? Is that what you're
Yes. Yes.
Yeah. So in these animations, it's a great question. In these animations, we're always showing things in a scale such that it looks like, oh my gosh, we're going to hit something all the time, right? And then you see movies like The Empire Strikes Back, where the Millennium Falcon's careening through the asteroid belt, and oh my god, it's going to crash into something. But it turns out that space is really big and these objects are really small. So when we design missions, it's not so much of can we avoid a collision, but can we actually find anything to encounter at all? So we're pretty safe in terms of asteroids, but there are really, really small things they call meteoroids or micrometeoroids. And they actually hit spacecraft. And actually, when you look at, let's say things that have been up a long time, like the Hubble Space Telescope, it's actually experienced a lot of micrometeorite damage over time. And when we send astronauts to the moon, if we want to build a base there and the rest, this is something you have to worry about. Will the micrometeorite hazard over, let's say, some period of time be threatening to the asteroid? So you have to build shielding and the rest. So very, very small things are probably our biggest worry at the moment, rather than bigger things. But they are a worry, and we have to think about it.
Thank you.
Sure.
The images from the Bennu project were phenomenal. How many cameras? What can you tell me about the cameras? How many did you have? And
yeah, I knew I should have put that slide in. I don't know if I can tell you a lot. I'm a dynamicist, so I don't know if I can tell you a lot about the cameras. If I'd have put it in, I would just read off the slide. I just don't remember. I think we had several different kinds of cameras. One was sort of a wide angle, and one was sort of a narrow angle to be able to do different things. So we want to be able to look at different. One to look at sort of the big picture on the asteroid, but also wanted to look at very narrow things on the asteroid. But beyond that, I don't think I can give you an answer at the top of my head. I just don't remember. I'm sorry.
No
the mission ended a bit ago, so my brain is now not working anymore for those sorts of things.
Brad, any more Zoomers?
But I will say, if you do a quick internet search on OSIRIS-REx, it'll tell you everything you want to know.
Oh, okay, cool.
I'm sure it's at Wikipedia. Wikipedia will have everything you want on the instruments.
And are the images public domain?
Yes, they should be. I think everything should be out there. I don't know where the easiest place is to find the catalog of all the images. JPL used to have a place called, I think the photo. JPL, I think it was called the Photojournal Catalog. But I don't recall off the top of my head. But it should all be out there. This is all owned by the public, right? So the public should have access to all these things.
It'll be a PDS, but that's, hard for non-professionals to figure out.
Yeah, I thought JPL had a place. I think they called the photo
It's
journal.
all PIO stuff.
Most of the place they had it's called the photo journal something, and I've gone there a lot of times to get released images, and I don't know if they have all the Benu stuff, but they might. And it's a great place for the public just to go and find great images. I've used it all the time for images in my talks.
Right,
So-
so that's something that was released as part of a press release. So it's gonna be the fun stuff.
Exactly. So you may have to do some searching. I think that's the best. I don't know what archive all that stuff is located right now, other than the planetary data system node, which is hard for non-aficionados to use.
Can I ask another question?
Sure.
Sure.
You talked about the iron metal asteroid. What is the composition of most of the asteroids that you have come across?
They're mostly rock. They're mostly silicates. Essentially a lot of the asteroid. A lot of the asteroids have the same kind of compositions that we found in our meteorites, because the meteorites themselves are just pieces of asteroids. So if you go down to, I think the Denver Museum of Nature and Science, I think they have a nice meteorite collection down there. You can even see things and get a feeling for what the actual asteroids are like. And also,
So the iron metal asteroid would be quite unique.
well, we have a lot of iron meteorites. Okay, so iron meteorites are very hardy things, and we think a lot of these iron meteorites have actually come from the cores of different worlds of differentiated. So whether we have a sample of Psyche or not, I don't know. We're actually debating that on the team right now. There are certain kinds of iron meteorites which actually might be a great fit, but it's hard to know for certain whether a given iron meteorite fits well with Psyche, because the spectroscopic signature they have is a little nondescript. So we're gonna have to wait, I think, for a few more years to find out.
Another question.
Sure. Go ahead.
Excuse my ignorance, but I'm just
That's
very
fine.
curious.
That's fine.
What is your speculation of how the galaxy and universe was created? I mean, you talk about how big space is. I was surprised by your answer. I was
I would say, okay, so I did not talk about the galaxy. I talked about our solar system. I didn't talk about our galaxy, and I didn't talk about the universe. I think cosmology is something I don't think about a lot. So I know about as much as like a typical layperson. I think the idea is that our universe probably formed in what they call the Big Bang, which would be sort of a giant cosmological collision, or sorry, explosion, where our universe may have started as a surprisingly small, what you call it, object, thing, or what you want to call it. That seems to be the easiest way to explain certain constraints we have in terms of the background temperature of the universe, why we have structures. A lot of the structures we have that ultimately formed up galaxies came from that initial Big Bang experience, where we end up with clumping of material around in different places that ultimately became galaxies. That's what I think is going on at a really, really hand-wavy situation. I don't know if I can say easily more about that without having to think more about it.
All right. Anything from any other Zoomers? All right. Well, before we do one last thank you, I want to mention that Wings on the Rockies, the Air and Space Museum, produces a show called Behind the Wings, and it's aired on PBS. And it just so happens that this week's episode was on OSIRIS-REx.
Oh, fantastic.
So they did a 30-minute thing on it. It's not as good as what you just saw, but you might want to check it out. So, all right, thank you. Thank you very much. All right, let's find that audio and play the play Ringo here.
Ringo. It is fun that we got.
All right, so you know which slide to go to here by any chance?
Oh, the one with Beetle on it.
Yeah.
No, I went too far. Let's go back a little bit more. I think it's right there.
This guy here.
I think so. Yeah, let's try that.
All right.
So I think if you make it, I think you have to play it because it's an animation. So you have to try to press it.
Oh, okay. All right, that's no sound. That's not good. Well, you guys aren't seeing it, so, oh, because I didn't do slideshow.
It's really amazing. It's not producing any sound at all.
Yeah, I don't get that.
You're not muted.
And we've been hearing the speaker.
Yeah, when we first started. I mean,
Yeah.
are the Zoomers still there?
We're here.
Oh, okay. Just we're trying to figure out the sound. They want to hear the sound in the room.
Output device, that's wrong.
Ah, there you go. So I wonder if that was it.
I don't know how you're hearing the Zoomers, but.
Let's so go to full screen and see if that works.
Trying to go to the.
Or you can just hit play too. Let's just see if that. There you go.
All right.
All right.
I want to get it up on the big screen here. So. I'm just gonna drag this out.
Okay, so go ahead and hit play. And if you want to, you take it to full screen, that'll be fine too.
Well, just.
Yeah, just do
Just do that.
A little noisy, but I'm so excited. Lucy is going back in the sky with diamond. Johnny will love that. Anyway, if you meet anyone up there, Lucy, give them peace and love from me. And NASA, peace and love. Don't forget. Don't forget, my name's Ringo. Peace and love.
Right.
What wishes was that an advertisement?
Can you do the launch too?
That's what I'm thinking too.
The launch is mostly just people cheering. Just
We like people cheering. Is that playing? No. Oh.
It's in a rocket, was it?
It was an Atlas.
Atlas 5.
This is so cool.
Yeah.
It was an amazing launch. The nighttime launches are clearly.
Love the practice.
How far away were you? Dewey, did you see that launch?
I did not. But I can vouch for how cool that was. Even compared to a space shuttle launch at night and a Saturn V launch at night, the way that broke through the clouds was really cool.
Yeah, you're asking on distance. I think we're a few miles away. This was they have a place that's sort of very. If you've ever been to the Kennedy Space Center, they have a place where they have the Saturn V, where you can go visit. Right by the Saturn V, there's some viewing stands, and the rest that's where we were sitting for this.
Oh, yeah.
So I think would you say that's a few miles to the launch site to that
3.5.
3.5? Okay.
Well, I think it's 3.5 to the press site.
Well, yeah, that's near where the Saturn V is, though.
Oh, is that over by then?
It's near the VAB and
Oh,
press site. Yeah.
yeah,
They have a whole bunch of bleachers there for just
Okay.
things, right? So
yeah. Come to think of it, for a launch like this, he probably was at the press site. So that's cool.
They call it the VIP place, but
It might be a little bit.
it's probably had about 5,000 people there, so we're all VIP.
All right. Well, thanks.
Can I ask one more question? Just a piece of advice from the speaker.
Say what?
may I ask a piece of advice from the speaker?
Oh, yeah, I'm sitting.
Yeah, he can hear you. He's at the back of the room, but go ahead.
Well, I just love everything you're working on, and but I have no engineering background, no science background, no very little math background. How could someone like me ever be involved in some of the nature of the kind of work you are doing, or in just space work?
Well, I mean, there's all sorts of ways. I mean, are you interested in just, let's say, I mean, there's always things like education and public outreach. Is that what you're interested in?
Oh, that is a possibility, but there aren't many programs in education.
Well, what I'm wondering about is that, every now and then, I'm just speaking off the top of my head, I've seen like at the Denver Museum of Nature and Science, they have like docents, right? And the docents educate themselves about various missions. And then when people come and visit, then they talk about that to the public. So that is something you could do. Would it be interesting to you?
She's back from DC.
Oh, well, in DC, you have the Smithsonian. So like the Smithsonian can do all sorts of things. But I think there's
Well,
also,
those are mostly volunteer jobs. What about jobs literally where there's a potential salary involved?
Good luck.
yeah, I mean, is Bob still here?
What is Bob?
He got fired.
No, if someone is in DC and they want to be interested in working somehow to, let's say, do things with NASA, but they don't necessarily have like an engineering or science background, what would you suggest? You have a good idea?
No, it's not bad.
I mean, I think there's a lot of ways to get involved with NASA, but I think probably the thing to do in DC is to see maybe contact them and see what they have available. I don't know off the top of my head because I don't, I'm in Boulder, not at NASA headquarters, but I think that they're always interested in getting the public involved with different things. And I think as a volunteer, if you actually want a salary, then I think it depends on what you can do, what your qualifications are that could help them. So
And in the Boulder area?
Well, I think it's the same thing. Like, so for example, like in our office, we have a lot of scientists and engineers and the rest, but we also have a lot of support people that help the scientists do their things. But I don't know if that's the kind of thing you're looking for, though.
Yeah, that sounds nice.
Oh, okay. So,
All right.
I mean, it's just a matter of what a support person does.
Right.
well, some of it's paperwork, unfortunately. So I don't know if that's what you're interested in. But some of it is paperwork and helping scientists be able to write proposals or turn in proposals that get the funding to do their science. There's always infinite numbers of things that need to be done in our office or other places. So, but it would be again helping scientists, helping engineers do their work by helping them with the morass of paperwork and everything else that they have to do. Meeting organization, all those sorts of things.
Thank you.
Sure.
All right. All right, let's move on to Leonard's show here. Leonard, wake up. Okay.
You still okay? I won't be long. Hey, there was a lot happened in the last 24 hours.
There you go.
Okay. Let me start. I have a new hat because Barb hated every hat that I had. They were old and dirty. So I had to go and get a new hat. The thing that's really, I write about space for a couple publications, and the thing that's been really interesting is the Chinese. I always follow them very, very quickly and follow them all the time. They have a very interesting problem up there. The crew that was
I gotta share some screen again.
Okay,
I'm
I'm
just
not
so
touching it.
forgetful.
all right, what do I gotta do?
I'm just sit tight.
Okay.
Tricky that.
China has a space station. They launched a crew, and it's going to be hard to follow this because I had trouble with it. They had a crew that just launched called Shenzhou 21. to replace the Shenzhou 20 crew. They had been up there for about 6 months, and everything was fine. And then apparently when they were ready, the Shenzhou 20 crew was ready to leave the Chinese space station. They got into the capsule and they realized there was a crack in the window. Okay, well, the window is part of the return capsule, and they reported this, and apparently they were going to come back on November 5th, and ground control goes, I don't think so. We're going to hold off. We're going to go analyze this. How bad of a problem is it? And they were up for about a week more on the space station, which is not really designed for a long-term 6-person crew. They're eating the oxygen up, they're eating the food. So they had 6 people up there for a week longer than they thought they were going to bring this one crew down. And so what happened, it's pretty interesting because it gets to something that it's going to haunt human spaceflight. And hello, yeah. So it's going to be haunting space flight.
Advance the slides.
I will.
Show the Chinese.
Oh, the Chinese thing. I don't know. Okay, there we are. Oh, there they are on the right. 6 people are jammed in there. And it's not a big space station. I mean, it's adequate for what the Chinese are doing right now. They're going to build on that in a little bit. But anyway, okay, so you have a situation where you got a busted spacecraft with a window that they don't want to have the crew come down in because something could be catastrophic. So they decided to use the spacecraft that the other crew just got there, Shenzhou 21. Yeah. And so they said after a week, okay, you guys come back, but use the other spacecraft. So, okay, they were able to do that. They came back. They just landed the other day, yesterday or 2 days ago. Everything's fine. Now you've got a crew up there of 3 people that have no way home because the spacecraft that's hanging on their space station is broken. And this gets to a much larger issue that I'm really focused on right now for a bunch of stories on space rescue. At some point, we're going to have people stranded. This is a close flyby of the problem. And the problem is that, space stations, China has a different kind of space station. They're in a different kind of inclination compared to the International Space Station. Also, there's problems with docking adapters. If there was people stranded, if there are people stranded up there, can we go get them, have compatible docking? We're not there yet. And this is what I think is one of the early warning signs of if we're going to have humans up there doing things in space, we better get together on collaborating between countries on standardization of docking adapters, rescue technology, be more forthcoming. China was a little squirrely on trying to tell people what happened. They didn't say anything about why they didn't want to bring this crew down. Only later on, it was revealed that there was a crack in the spaceship window. And it's not something unique, Actually, the shuttle and the International Space Station has been hit by space debris much similar to this situation. And I'm digging into that because I'm fascinated by the future. How are we going to get compatible with other countries that are going to be up there? And there's a lot more countries coming. Russia's going to have their own space station soon. India will have their own space station. We'll have private space stations up there. And so how do you move between all these situations of having humans in space and being more careful? And as one of the things that somebody beat on me the other day, we do this in maritime. We do this with submarines. When we lose a submarine, there are ways to rescue submariners, and they went through a lot of years of losing submarines with people on board. It's somewhat of an analogous to what we're facing in space. Anyway, that's my lecture on that thing. But it's pretty interesting. I really love this. And on the positive side, and not to discount, let me finish the Chinese used that spacecraft to get back down. They just landed the other day. The three that were been up there for 6 months, they came back down safe and sound, but on the new fresh spacecraft, brought back a whole ton of experiments that they had been doing on the space station. So everything's fine. They're in Beijing now and being saluted for their bravery and all that. But anyway, it's something to watch and how this is going to evolve. Meanwhile, we had a really interesting thing. I love anything that's going to challenge Elon Musk and SpaceX. This is one. Jeff Bezos, another billionaire, trillionaire. They had a great mission the other day, 2 days ago, a couple days ago, and what they call the New Glenn vehicle. It's pretty powerful. It's a big vehicle. This was the second flight of it, but this one, they were able to successfully land the first stage like Elon does on a barge out in the ocean, and it was all successful. It was great. Plus, they were able to throw with that launch what they call the Escapade twin spacecraft toward Mars, but it'll take a while to get there. They're up there now. They're apparently healthy. Everything went really well. The whole mission is very, at least the way I get it, it's been very successful. And Elon Musk had a great mission. That happened when did I say it here? October. In October, he had another Starship flight of his own vehicle that is, really pushing the boundaries of technology. Great flight. Is probably the most successful one he's had. So he's in the running, like Jeff Bezos, for reusable, huge rocketry, changing the dynamics of space transportation. Both of these guys are moving forward. This flight for Elon Musk and the Starship went very well compared to some of the other problems they've had. Elon Musk is great on saying, fly a little, learn a lot, blow up stuff, whatever we get out of it, we're going to move forward. And he is moving forward to the next Starship Flight 12. That's coming up fairly soon. And anybody that wants to watch, the thing that's amazing to me as a kid when I was growing up, when I was watching Kennedy Space Center develop, there was no Kennedy Space Center. And to watch the evolution of the Starship takeoff point in Texas, it's amazing. These people are working night and day to build up a huge launch complex. It is pretty impressive what Elon Musk is spending as far as his money into a ground infrastructure to launch these vehicles, bring them back to the actual launch area. I don't care if you hate them or love them. It's really something to watch. what he's doing. And my guess is he's going to have a lot more problems, but it seems like he revels in any kind of problem and he's going to try to fix it. Because one big thing, he's in a big race to get NASA money to make sure that starships are used on the moon. And this is an artist concept. This is about these people make more money on space travel, the artists, than anybody, because they can draw anything and it makes it look like it's all routine. But anyway, here's some starships that have landed on the moon. This is Elon Musk. This is a SpaceX drawing. But anyway, we're kind of in a really interesting point in time about getting to the moon with reusable rocketry and maybe less money. NASA has bought into this, but there is an issue coming up with that. I'll tell you about that in a second. But anyway, it's great. It's I don't know what's going to happen. It's so much fun. I'm having so much fun. Whether they blow up or they go right, it's journalism. You write about it and you have a lot of.
So the artists and journalists are making money in space.
That's right. Maybe the journalists are making more money than the artists. I don't know. Probably. Anyway, in the middle of all this, NASA just got back in the groove. Everybody I've talked to that works at NASA or for NASA or has a contract with NASA say, oh, they're back on the phone. I'm getting phone calls. Okay, well, the government shutdown has taken effect, but we went through a pretty good lengthy period here with the government shutdown where you got Bill Nye, the wise guy, up there, trying to save NASA science because we're worried about with the budgets and what NASA is going to be doing in the future. Meanwhile, the guy that Trump hated at one point, Jared Isaacman, who has flown in space on a couple times now himself, is back in the groove. We had a transitory NASA administrator, Sean Duffy, who was acting administrator for NASA, but also was the FAA guy. He was running the FAA.
No, Department of Transportation.
Well, yeah,
It
okay.
includes the
Department of
FAA.
Transportation and the FAA in particular, because we all experienced the flight delays. And, NASA got off of Duffy and actually hired, looks like they're going to rehire or put in place Jared back that Trump didn't like at first, and now he loves him, I guess. But we'll see. And it has to be confirmed we have to go through the confirmation process. But meanwhile, NASA to me, when I phone people, it's still in turmoil, and we got a lot of issues about the budget. There's a lot of concern about how much money all the space program costs, and where we're headed. So, it's one of those TBD.
I think you're 15 minutes.
Oh,
It's
oh.
almost over. No, we've got other people.
Okay.
5 other people.
Okay.
Up there if you can move a little fast.
Okay, that's good. I'm ramping now. I'm kind of mad about everything. Okay, then let me just go through this real quick. In Australia, we had a space debris come down from a Chinese rocket landed in Australia. People are upset. It's really interesting. More space debris coming down. Watch your head. SETI, very interesting new development between a provider of AI and the SETI Institute to help sort out radio signals. And I think keep an eye on that. This is a turning point. We're going to have much more knowledge about signals from space that could be ET. And again, I'm a UFO fanatic, UAP. There's a movie coming, pretty good. I've seen pretty much all of it. probably one of the better ones about trying to figure out flying saucers, real or you imagine UAPs. What are we talking about? Are we in a mode of disclosure about any kind of contact with alien craft on the Earth? And then the biggest news really was local. We had aurora. There's comets flying by. I can't keep track of it. I mean, there's some great stuff happening. We had a great, Barb, you can pipe in,
Yeah.
and Dewey. We had a great thing out at the
This planetarium.
Fisk Planetarium.
Was our last meeting.
Yeah,
About 8 of us showed up there.
yeah. Well, there's a lot of people showed up, and we got a bunch of people out there to look.
International Observe the Moon Night. So
We did that.
after the show and did this. Didn't see that.
We had a good time out there. It was a good event, and Dewey brought. What did you have? You had a
Big binoculars.
11 by 70 binoculars.
yeah.
And the clouds parted.
And the clouds parted. We prayed. The clouds parted, and then Halloween came, and we did our bit. We had a telescope out in the
I
deck,
handed out that sky calendar to about 80 kids.
and we had we had the most people fly by our for Halloween candy. We ran out of candy. No, I got a couple of Tic Tacs, don't I?
Yeah. Yeah.
Okay, and here's from Y. Chapman.
Yeah.
And let's talk about the aurora, because Y got a great picture and a lot of people in the area did. That's enough for me. I'm sorry.
All righty.
All right.
Questions for Leonard before we move on?
No more questions. I'm out of room.
Okay, so what we have next is I got some pictures that John Aswell has brought, so I'll get those up so you can see them. And then we'll be turning things over to John Williams, who has some pictures that other people may have had.
You doing okay, Bill?
Yeah.
You okay? Don't go longer. We want to get a group picture at the end, so.
Okay, thank you.
Oh,
There we go. Okay, thank you, Dewey.
All right.
4 weeks ago, I went down to something called the El Dorado Star Party, which is in kind of West Texas. And it's not a highly advertised or extremely highly attended star party. And it's a couple 2.5 hours west of Austin, but at about 2,500 feet. And why did I go down there? Well, I haven't been to a star party for a long time. And also the weather is pretty nice that time of year. And I had 3 good nights in a row, and it was all good. Did mostly visual observing. Okay, thank you. Next slide, please. And Dewey, I'm glad you showed this one first, because it's not as good as one we're going to see later. There's Comet Lemon, and you can kind of see the ion tail out to about there. And here's for reference Arcturus and some of the other stars in Boades and the Kite. So yeah, it was visible naked eye. Those are 2 short exposures on a tripod only. And it was visible naked eye for about 15 minutes before it got too low. Seems to be a little bit of air glow going through the picture, but yeah. Anyway, next please. And another 2 short exposures. But yeah, that's how the sky quality is down there. Not too bad. A little darker than up here, but not tons. But yeah, I think the Milky Way is better down there. Of course, it's higher also. Okay, next slide. We were right in the middle of a mass monarch butterfly migration, and I haven't seen monarchs for so long. But yeah, there was one or two coming by every minute. Heading south too. Get next, please. and they were all over the place. I don't know what kind of food they're eating this time of year, but yeah, we're really busy. Okay, next, please. Not a monarch butterfly. There are a lot of those too. Okay, thank you very much.
All right, so John Williams, you would be up next.
Okey-dokey. Jim, you're up.
Okay.
So we have a few things. We've got Jim going to talk about some balloon stuff, and then we've got Aurora, and we're going to finally end with some very nice videos to set the tone. So there you go.
Okay, we'll do a little tiny.
No, it's,
It just disappeared.
no, it's up in the corner. I only have about 5 minutes here, so. I'm a member of I'm a ham radio operator. And I learned about this actually from George Lemkel up here in the canyon. But we have a club called Edge of Space Sciences, and we launch high altitude scientific balloons. Mostly they're latex balloons about 9 feet in diameter. They go up to 100,000 feet pop, come back down on a parachute. And we carry up payloads that students have built in various aerospace programs.
We're seeing it on Zoom.
Yeah.
It's trying to go full screen.
John, it's very tiny up in the right-hand corner of the screen.
Where it probably.
Are you seeing my whole screen or just the part?
Yeah.
Getting
Does
closer.
that make it?
How's that? There we go.
Hold
Okay.
on. That shouldn't have been. I'm sorry, you saw my whole screen there. Sorry, let me share this again. All right.
Okay, so we normally launch these big balloons. In fact, last Saturday, we launched for Colorado Space Grant, which is NASA finance program for colleges all around Colorado. That's what we mostly do, but we've recently got into pico ballooning. What happened is back in the 1980s, amateurs were flying balloons with radio transmitters on them. And pretty soon they decided they blow out to the east and they were starting to go across the Atlantic Ocean. And so some amateurs were trying to figure out how can we get a balloon all the way across the Atlantic. And they had this complicated payload that had ballast on it. So when it got cold at night and it floated down, they could let water or antifreeze out of it and it would go back up. And then somebody figured out a low-cost way to do it is to use a Walmart party balloon and an ultralight radio transmitter on it. So what we are doing now, and I never helped invent this stuff. I'm kind of standing on the shoulders of giants. But what we've got is a 36-inch plastic balloon. It doesn't come from Walmart. And then we have an ultralight solar-powered radio transmitter. That transmitter and the antenna weighs 15 grams, which is about half an ounce. Okay, and on a party balloon like that, it has a 34-foot antenna that hangs, and it hangs right in the middle of that. It's a dipole. And so that's the thing we're gonna fly. Next slide. Okay, there's the pico balloon when we launch it. The plastic balloon, and now it's here on the ground. It's a 500-liter balloon, and it only has about 80 liters of hydrogen in it. And as it goes up, it expands. And when it gets up to 45,000 feet, it goes tight, and then it'll just float along at that altitude. So here we are launching it with its long antenna. Next slide. And there's the balloon sitting in my Radio Shack. I blow it up with air and stretch it so that it flies a little bit better, but that's the size of the balloon. Next slide. And that's the radio transmitter. Now those are my fingers up there, and I don't have really big hands. But it's solar powered. Those are plastic solar panels, 0.5 millimeter thick circuit board, and all sub-miniature parts. surface mount parts. A guy in Alabama builds these things. Okay, so
No
next
housing?
slide. Next
No
slide.
housing?
No housing. It's just a
Okay.
bare board.
Okay.
Flying, and it's up in the stratosphere, so it's around 0 to -10 degrees Celsius. It's not real cold. Okay, so the thing when it starts out, we launch it in Colorado, and the red dots are when it actually is reporting information. There's people all over the country that are set up to receive these signals, or amateur radio signals. And when they receive the signals, they put them onto the internet. And so we can go to the database on the internet and see the location of the balloon. The red dots are where it's transmitting during the day. And then when the sun angle gets down too low, it stops transmitting, and at night it doesn't transmit. So the green lines are connecting the dots between the days. So it transmitted real good during the day for the first couple of days. And then as it goes out over the ocean, it's either not transmitting as well, or people are not able to pick it up because there's people that aren't close by. This balloon does actually have some transmitter problems. I think the antennas are screwed up. But anyway, every once in a while it will report where it is, and you can see it goes across the Atlantic Ocean. It went down to the south, and then it ended up circling around in the doldrums, or whatever you call it, up at 45,000 feet for a little while, and finally came out of that, and it headed up over North Africa. And once it got over North Africa, there's a lot of hams in Spain and France and Italy and Turkey. So it picked it up pretty good there. Next slide. Okay, so it went across North Africa, and then it came right down the Mediterranean Sea, right across Israel, and then up through the Middle East. Notice there's a big, long trail there where we didn't see anything. What happened was it was coming across Israel, and then all of a sudden, magically, it was sitting on the ground at the Queen Ali International Airport in Amman, Jordan. And it sat there for 3 days transmitting. Now, this thing isn't going to transmit when it's sitting on the ground, but that's where we reported where it was. And then all of a sudden, it magically appeared over central China 3 days later, back up at 45,000 feet. And what that was somebody is spoofing the GPS on that thing. We have seen that in the Middle East. We've seen the Russians do it, and a little bit of the Chinese doing it. But anyway, so it spent some time in Amman, Jordan. Okay, came over central China, a few reports, and it reported pretty good when it was over. It went right over Beijing, right over North Korea, both at night, fortunately. And then it went over Japan. Next slide. It continued on then across Japan, across the Pacific. It hit some doldrums in the Pacific, and was actually going across the Pacific at 35 miles an hour. And I pointed out it's going to take a long time to get across. But somebody said, the Pilgrims in their sailing ships would have loved to be able to go on 35 miles an hour. They crossed the Pacific. The map wraps around. It's coming across the Pacific. Next slide. And it finally finished its first lap around the world.
Wow.
This took about 3 weeks to do it the first time because of the doldrums that it hit, but it kept on going. So the next slide. Okay, so there it is going across. Notice it's a little farther north this time as it went across. And actually, if it gets up too far north, the sun angle never gets steep enough onto those solar panels. So bigger solar panels would work, but that would weigh more and it would fly lower. And the catch is if you fly too low, you'll run into thunderstorms. Most thunderstorms go up 45,000 feet. Every once in a while, some will go up to 50 feet. So that's eventually what will kill this. But it started its second lap around the world. And then the next slide, which I think is my final one. That's where it is today, 3 laps around the world.
Wow.
And it's still going.
Wow.
Last time I took a look, it was actually right out here off the coast of Japan. What is that? The Kamchatka Peninsula. Right there. Haven't heard from it for a couple of days. It's hopefully still going. And John, do I have one more slide? I do. Yes. And it turns out we launched this balloon on September 18th, and it's done its 3 laps. It's on its 4th lap around the world. And then on October 23rd, we launched 2 balloons from Grand Junction at a ham radio conference. And those 2 balloons have each completed 1 lap around the world and are busy on their 2nd one. So anyway, a fun part of the hobby. You know, the whole sum total of the scientific aspect of this is the fun of having a balloon that goes all the way around the world. It does report temperature, and one of them has a relative humidity chip on it as well. But it's a lot of fun. Let's go.
Okay, John, you know who's next. Go ahead.
Yeah.
David, come on up.
Okay, we can do first slide. I've talked about my little telescope in New Mexico that's optimized for looking at faint nebulae in the galaxy, but we've also picked up planetary nebulae that had never been documented before. And this was number 7 that we've registered. And this was about a month ago. One of the colleague, Dana Patchik, looks through surveys. WISE survey, Pan-STAR survey, Bill, that you referred to, and also Palomar surveys, and looks for faint blobs that other folks had not picked up on, and sends these off to me and say, look here and see if you can see something. And 90% of the time there's nothing there, but occasionally there is. Let's go to the next slide, John. That's not the next slide.
It is. It's
the first presentation. Okay, keep going. All right. This is not the presentation I was talking to.
Sorry.
What is?
Just make something.
So I can make it up as we go.
I'm sorry, David.
In the late 40s, early 50s, the 48-inch Schmidt camera at Mount Palomar surveyed the sky on glass plates. And one of the surveys that Dana Patchik looks at is from those Palomar plates. And this particular object that we first showed was kind of a smudge on one of those plates. Well, it's a 48-inch telescope. I have a 4-inch telescope in New Mexico. How can I compete with that? Well, the 48-inch has 144 times the aperture I do. So that's where we're starting. But the camera on the 48-inch used film that sees about 1 photon out of 20 that arrives there, whereas a modern CMOS sensor sees almost every one. So I pick up a factor of 20. The Palomar camera used a red filter. And so it looked at a big chunk of the spectrum, say 100 nanometers wide. What actually was causing the light was a tiny little bit of emission from hydrogen atoms and a little sliver of that. Well, I observed through a filter that's 3 nanometers wide. So I pick up a factor of 30 advantage over what I'm looking at relative to the background. And then finally with film, you take a 10-minute exposure, 20-minute exposure, looking through your guide camera, playing your video game, keeping your stars centered. And that's it. There's your plate. Well, I take another 10-minute exposure, another 10-minute exposure, do that all night. And, well, let's just do it the next night too. So I can pick up other factors of 10 advantage over the Palomar Schmidt camera. So I'm able to see these planetary nebulae that had been barely detected before, but now we can see details in them. And since that was 7, then 8 and 9 over the last couple of weeks. And then I'm working on 10, 11, and 12. I've got 30 hours of exposures on item 12, but those haven't been submitted yet. But these are just a byproduct of taking pictures of pretty nebulae in the galaxy.
Yeah.
What you got next, John?
So I appreciate everybody who sent photos in. And you know, it was nothing short of spectacular. But Judy included this the other day, this cloud that hung over the Front Range in her little moonshot. But what everybody was excited about was the aurora.
You want to say anything about that? No, everybody saw it. That's great.
No.
Yeah. Well, almost everybody sees it. That's the gross damn dam. Very gross, very damn dam.
You know, I've seen pictures that direction from where we used to live. That is nuts, the light coming off. That's ridiculous.
It is ridiculous. They say they have to work at night. It's damn. Well, what was exciting to me was that it was naked eye visible, which last year was not. And this year it was so much more there.
David Polikanski sent this in. I think he sent it in from Santa Fe,
Yeah.
where I'm at.
That's where he is. That's amazing.
Yeah. So it's 7 o'clock down here, Dawn, she's like, people are seeing aurora. And I had looked at the aurora forecast that night, and it did not look that spectacular. It wasn't, just wasn't pushing this far south. I step outside and I'm just blown away by what we can see high in the sky. Anyway, Y. Chapman took this one from over, what's the neighborhood called? Where they live. Anyway.
Lazy Z Road.
Lazy Z Estate.
Right.
Yeah.
Lazy Z. And then Bill Bryant added this one today. I gathered from the bottom of Coal Creek Canyon, right, Bill?
Yeah, exactly. Looking up the canyon to the west.
Yeah, it was. And this is looking, we live on the kind of the west side of Santa Fe, looking north. Sangre de Cristos are there to the right. This was when it was getting really bright down here, about 10 o'clock or so. It was spectacular at that time. We could see those pillars, lots of detail that Judy was talking about. And I was surprised actually that we could see the green. The red is from particles lower in the atmosphere being charged up. Green is above that, so higher in the atmosphere. So that green is farther north. And then if you ever see blue aurora, which I haven't seen much of, certainly not down here, that's super high up in the atmosphere. Kind of a close-up of that area. It just looked like a light rays shining down from down here anyway. And what was interesting too is that at about 10 o'clock, there wasn't much going on straight north, but there was a lot going on to the east and the west. farther south. And I felt that was fairly spectacular. Ted Klein shared this from the Berthoud, the observatory up there. This is their all sky camera. And let me stop sharing for a second. And we have two more things. We have a video from Ted, from Ted sent of this thing down here. Hopefully it plays well. Okay, let me make that. Oh shoot, hold on. Stop that.
What you said, why I'm changing.
All right. Play this video. This is the all night long from Berthoud. There was another event yesterday, an X5 class flare, which was just as powerful as the one that caused this aurora. The sunspot group, or the group of sunspot group that created the Tuesday's aurora, erupted on Sunday, and it was facing, it rolled that material toward us. This event that happened Friday, it'll graze the Earth, and so maybe tomorrow night, check the NOAA's .gov's website for aurora prediction, and there might be another great chance for aurora tomorrow night. All right, and this last video is from Mark Peterson. That is it.
And our professional planetarium show creators, that's why it's.
All right, John, is that all you got there?
That's all we got. Thanks, Mark. That was awesome.
Yeah, and thanks, John, and thanks for all those people who sent in that neat stuff. That was cool. All right, so that's the show.
Mark, you got some?
I was just going to say that was my usual 10-second comet exposures, and that was too much. The aurora was too bright, so I'm going to have to back them on down next time. Maybe like 5 or 6 second exposures.
Okay. By the way, did any of you Zoomers have something on your computer you wanted to share with us tonight? I'll take that as a no. All right, so that's the show. Good night, Zoomers. And here in the hall, we will do our picture and then we'll put away the chairs.
Thank you.